The next question. This is a long example. Find the domain, range, xy intercepts if any, asymptotes if any, symmetry or period if any, first and second derivatives, intervals of increase, decrease, concavity, and then sketch. Okay, so a whole bunch of things. What's the function? Function is natural log x squared plus 2x minus 15. What's the domain? Well, so every item, right? Domain. Well, argument of natural log must be positive. In other words, the domain of natural logarithmic function is open 0 to infinity. Therefore, domain of fx, that is natural log x squared plus 2x minus 15, it is a set of those real numbers for where the argument is greater than 0. All right, the object inside must be greater than 0. Well, what is this expression? If you notice, it factors. It's x plus 5, x minus 3. So if you look at this carefully, you can view it as a parabola that opens up with intercepts at negative 5 and 3. So where is it positive? To the left of negative 5 or to the right of positive 3. So the domain of fx is negative open interval negative infinity to negative 5 union open interval 3 to infinity. Okay, so that's your domain. Now let's understand the range. As x approaches plus or minus infinity, remember you have two branches. You could go to positive infinity or negative infinity. Either way, this polynomial, because of the highest power is positive with positive coefficient, either way x goes to positive infinity or negative infinity, the overall the limit of the polynomial is positive infinity. Okay, and that is because you have an even highest power with the leading coefficient positive. So you know that this polynomial goes to positive infinity. Moreover, let's look at 3. So 3, x minus 3 is a factor, you see. So as x approaches 3 from the right, this function polynomial approaches 0 from the right. Okay, so I hope maybe I could draw a small figure for you to understand. We are looking at just the polynomial, not the logarithm, just the polynomial. So the polynomial has intercepts at negative 5 and positive 3. Okay, so pretend this is, 3, right? And because the leading coefficient is positive, my parabola is going to open up. So it's going to look something like this, okay, roughly. Now, you see, there you go. You see what happens then. When x approaches 3 from the right, my value of the function approaches 0 from the right, from the top. That's all we are saying. Likewise, when x approaches negative 5 from the left, my value of this parabola values, they come down from top. So 0 from the right. Now that's important. In other words, look, the range of these, this expression is from 0 to infinity, positive 0 to open interval 0 to infinity. Okay, both these branches. Therefore, natural log itself, the argument is ranging from 0 to infinity. So my function fx lands in negative infinity to infinity, because that's what natural log does. Natural log does the following, right? So when you're On the interval 0 to infinity, natural log goes from negative infinity to positive infinity. So the range of my function fx itself is the set of all real numbers. Okay. What about intercepts? Well, to find the x-intercept, you set y 0. Well, that is y 0. So if I set 0 here, natural log is this. When does natural log becomes 0 anyway? It's only at 1, number 1. In other words, the argument inside should be 1. Move the 1 here, that's negative 16, so that's a quadratic. All we use is quadratic formula, assuming I have used it correctly. There are two values of x, negative 1 plus square root 17 and negative 1 minus square root of 17. I've simply used a quadratic formula. That's when I get intercepts, x-intercepts. How do you find y-intercept for anything? Well, to find y-intercept, you set x 0. When x is 0, that's 0, that's 0, I left with negative 15. But negative 15 is not in the domain of natural log. So, there is no y-intercept. How do you find asymptotes? As we have already seen, as x approaches 3 from the right, this expression, this polynomial goes to 0 from the right. As x approaches negative 5 from the left, my polynomial approaches 0 from the right. Therefore, when x approaches 3 from the right, natural log of this expression approaches negative infinity. Likewise here. So you see, as x approaches 3 from the right, my polynomial approaches 0. Polynomial is the argument of my function f. So as this approaches 0 from the right, my natural log goes to negative infinity. So that happens at 3 going from the right and at negative 5 going from the left. Either way, argument for natural log is going to 0 from the right. So natural log value itself is going to negative infinity. So we have x approaching 3 from the right, natural log of my polynomial is negative infinity. Limit x approaching negative 5 from the left, natural log of my polynomial is negative infinity. Therefore, x equals 3 and x equals negative 5 are vertical asymptotes, you see, because I'm hitting an infinity, a positive or a negative, in this case both negative. Whereas when x approaches plus or minus infinity, my polynomial goes to infinity, so natural log also goes to infinity, right? When x approaches plus or minus infinity, my polynomial goes to positive infinity. Well, as my argument goes to positive infinity, my log also goes to positive infinity, which means I do not have any horizontal asymptote. What about symmetry? Fx equals natural log x squared plus 2x minus 15. Let me change sign of x. When I change sign of x, I get x squared minus 2x. Okay, that continues to be x squared, but this becomes 9 minus 2x minus 15. Therefore, f is neither even nor odd. This function is neither symmetric above the y-axis nor above the line y equals x. Further, f is not periodic. It is not. It simply goes to infinity. Okay, increasing function. Now, let's look at fx. I want to find the first derivative, second derivative. Natural log x squared plus 2x minus 15. First derivative, that comes down, derivative of the top. 2 times x plus 1, x plus 5, x minus 3. So important intervals, negative infinity to negative 5, 3 to infinity. What about this? Negative 1 could have been a critical number, but it's not in our domain. So you see that's between these two, negative 5 and positive 3. So it doesn't give us anything. We are looking at these two intervals. Choose a test point. Find the sign of f prime. Here it's negative, here it's positive. So I'm decreasing in the first interval and we are increasing in the second interval. Now, let's take the second derivative. You could take the second derivative of this, or you could find the derivative of this, or you could use properties of logarithmic function. Take your original log of a polynomial, factor it. That splits your log into sum of logs. So first derivative is simply 1 by 1 plus x plus 1 by x minus 3. Notice using chain rule, derivative of x minus 3 is 1. Derivative of x plus 5 is also 1. When I take second derivative, I just need to take derivative here and derivative here. So that's negative 1 over x plus 5 squared minus 1 over x minus 3 whole squared. So keep the negative out. Combine common denominator, x minus 3 squared plus x plus 5 squared, open and open. Don't forget it's negative throughout outside. At the end, I have in the numerator 2 common. I'm left with x squared plus 2x plus 17 when I factor the 2 out. But notice the numerator. It's nothing but x plus 1 squared. That takes care of the first 2 terms and 1 from here and 16 left over. Why did we do all this? Well, no matter what your input x, the numerator is going to be positive because I'm going to add 1 and square and add 16. Denominator is going to be is complete square. So everything here is positive. Outside I'm multiplying by negative. That means overall sign is going to be negative, less than 0. Second derivative is less than 0 for every x in your domain. So f is concave down on its domain. There are no inflections. We are decreasing in the first interval, increasing in the second interval. We have vertical asymptotes, no horizontal asymptotes, and they are both concave down. Okay, so this is your graph. We'll continue general logarithmic functions in our next video.